All right, well, I want to thank the conveners. Thanks for having me. I think this is a fitting location for this presentation to go, but I think it's a little contrasting with the more forecasting focus in this session that we have. So we're going to kind of change gears here and talk about forecast verification. And sorry, there's a lot in that title, and I kind of want to break it down here and start with talking about what actually I mean by a hydrometeorological event and a probabilistic forecast of that event. And the best example I can come up with is probability of precipitation. This is something that a lot of people in the general public will have come in contact to, because a lot of forecasts are framed in this way, and it's really the probability of precipitation, that precipitation will occur in a given day. And this is commonly forecasted by the National Weather Service and lots of other agencies, so I can't list them all here. But here's my example. This is a precipitation forecast for San Francisco earlier this week. And you can see we had rain in the forecast, and we have lots of different percentages on the 4 different forecast time periods. So those percentages correlate to what we think the probability of precipitation occurring. So that's a pretty general example, but we have a few other examples that I want to talk about. And one is probability of flooding. This is more of a research and operational type of forecast, and this is the probability that a flood will occur in a given time. And it's important for protecting against flood risk. And similar to the probability of flood, we can have the opposite probability of drought, the probability of that drought will occur in a given time. And it's important for planning water management and water use. So going forward, it's really important to decide what actually makes a good forecast. And I would argue that there's 2 primary aspects that we need to focus on, and that's reliability and sharpness. So when I say reliability, we want to determine if the forecast is reliability, and we're really asking the question, are the forecast probabilities representative of the actual event probability? So an example of that would be if we forecast an event of having a probability of 0.8, that will occur in 80% of the trials. So that relates somewhat to accuracy. And then we also have this sharpness, where we are determining how confident are our forecast probabilities. We want the most confident forecast we can create. And so we want forecasts that often give you probabilities of 1 or 0, and that's essentially a deterministic forecast, so that would be perfectly confident. But too often we have forecast probabilities that are closer to 0.5, where we really don't know. It's essentially a coin flip of whether the event's going to occur or it's not going to occur. So we'd like to avoid having that sort of situation. So now we have these 2 aspects, reliability and sharpness. And so how do we decide, should we focus on reliability or should we focus on sharpness? And so this forecaster assessment essentially becomes a multi-objective scenario. And I like this paradigm here, and it's pretty well documented in Nining et al. 2007. I'll give you that citation at the end. But the idea is maximizing sharpness subject to reliability. So we really can look at reliability as a condition for forecast acceptability. And then if we have multiple reliable forecasts, at that point we'll say, okay, we'll take the sharper one because we know that they're both accurate. And when you look at it from this perspective, it requires a detailed look at reliability assessment. And the thing that I really want you to take from this presentation is that conventional metrics may not be the most effective option when assessing reliability. So talking about conventional metrics, I would argue that the Brier score in terms of probabilistic forecast verification is the most conventional metric we have. It's very popular in both hydrology and meteorology. And there's many reasons for this. First is it's simplistic. You can see it's just the mean square error of the probabilistic forecasts and the observations of the events. It's also a proper scoring rule, which means that it's optimized only when the forecast is perfectly reliable and perfectly sharp. And this means that it gives us a fair comparison between 2 different forecasters. Another thing that is important about this is it can be decomposed into the reliability and sharpness metrics. But one caveat to this is that it requires binning. So you can see we have this big equation here where the Brier score can be decomposed. And on the left we have the reliability there, the mean square error of the bin average probabilities and observations. And then we have these variances and covariances, and that's really a function of the forecast sharpness and the observation uncertainty. So we have our reliability and our sharpness somewhat separated here. So we can actually focus in on the reliability component of the Brier score. And so there are three specific issues that I want to highlight about this reliability component. And the first is that the reliability component of the Brier score is a normal approximation of the binomial distribution. So it's an approximation, but the good news is that that error in the Brier score is approaches zero as we approach an infinite number of observation and forecast pairs. So you can see when we only have 10 observations, the error is non-negligible, but as you approach infinity, at some point that error is going to become negligible. So at some point, we won't need to worry about that. So that's the good news. But going further, the binomial distribution is an approximation of the Poisson binomial distribution. So with the binomial distribution, we assume that all of the probabilities in each of our forecasts is constant. But that's not the case. More often, they'll look like this in terms of these three synthetic cases that I've generated. So these are histograms, and on the left, you can see the probabilities are uniformly distributed. In case 2, they're biased towards 0. And then in case 3, it's kind of this U-shaped where it has a tendency towards 0 or towards 1. And if we plot the PDFs of each of these forecasts, you can see the Poisson binomial PDF in blue, the binomial in red, and you can see that at each of these cases, the binomial distribution is wider. And so that reduces our ability to distinguish between a reliable and an unreliable forecast. The final issue that I'd like to note is that the binomial distribution, since it assumes constant probabilities, it requires binning to approximate the Poisson binomial distribution. And so in doing this, we can bring up these same cases, and then I've generated these plots here where on the left-hand side we have the 95% significance interval width, and on the x-axis we have the number of bins. So I've separated each of these distributions into a number of bins, and you can see that the binomial distribution approaches the Poisson binomial distribution, but as we go to the right, the width of the 95% significance interval increases rapidly. So as that gets wider, we're reducing our statistical power. We're becoming less able to distinguish between reliable and unreliable distribution or forecasts. So I generated a few case studies for this, and these are all synthetic experiments that I'm going to present here. And so we have those three cases as I mentioned before, and then I want to compare the Brier score, the binomial distribution, and the Poisson binomial distribution, and examine the loss of statistical power associated with these commonly used approximations. So how I did this is I took 100 replicates of case 1, and I used that to forecast 100 replicates of case 2, where they have increasing skew and increasingly U-shaped. So you'll see here on the bottom left we have this reliability component of the Brier score, and on the y-axis we have the fraction of the 100 forecasts that are rejected, and on the x-axis we have decreasing reliability. And you can see as we move to the right, there's an upward gradient in those lines, and that shows that as the forecasts become less reliable, we're more likely to reject those forecasts. So that's a good thing. This is how we'd expect it to perform. But then when we look at the binomial distribution with a single bin, sorry for, I think this might be a Mac to a PC issue, but you can see that the blue line there is actually a steeper gradient than the blue line in the left plot. So this indicates that this binomial distribution in case 2 is actually more effective in rejecting unreliable forecasts. But you can see that on the x-axis, or that green line there, it just stays around 0, and that's another issue I'm going to highlight here in a second. But then this one on the right is the Poisson binomial distribution, and you can see the blue line is even steeper. So this is an even, as I mentioned before, an even stricter criteria for whether a forecast is reliable or unreliable. So this maximizes our ability to distinguish between these reliable and unreliable forecasts for case 2, and that's because case 2 is biased in comparison to case 1. And so with this single bin case, it actually works quite well. The issue though is that in case 3 is unbiased, and this single bin case is not sufficient because with that single bin case, we're only examining bias. And so what I've what I'm going to do here is go beyond this and develop a kind of a two-stage approach to applying this Poisson binomial distribution. And that is going to examine a single bin, as we did here, to maximize our ability to reject biased forecasts. And then, depending on if the forecast appears to be reliable from this first step, then I'm going to separate the forecast into two different bins, one from 0 to 0.5, the second from 0.5 to 1. And then, in this case, if the forecast is overconfident yet unbiased, each of these two bins will be deemed unreliable, and therefore we will be able to reject that third case that I was showing. So just as a proof of concept with this two-stage approach, you can see these are the exact plots we had before for case 2, except now they're all in the same figure. And you can see here we have the Poisson binomial and the two-stage approach performing quite similarly. And this is due to the fact that they are essentially the same on the first stage. So for case 2, they work essentially the same. But then when we go to case 3, you see the behavior change a little bit. The blue and red line, the binomial and the Poisson binomial distribution, still are unable to reject those unreliable distributions. But you'll see here the two-stage approach actually outperforms the Brier score as well. So in both cases, it's our best verification score. So to kind of sum up what I've gone over, the Brier score is approximate and determined reliability. That's something I want you to take home. That's for 3 reasons. It's a normal approximation of the binomial distribution. And on top of that, the binomial distribution is an approximation of the Poisson binomial distribution. And then third, it requires binning, which leads to a loss of information. This single bin Poisson binomial distribution is more powerful in identifying biased forecasts, but just using that single bin case is problematic when the forecast is overconfident and unbiased. And so I developed this two-stage approach to overcome these issues. It utilizes 1 and 2 bin applications of the Poisson binomial distribution, and therefore I'm stating that it maximizes our statistical power when examining forecast reliability. So with that, I want to thank you.
Are there any questions? Nika?
First of all, thank you for the weather forecast report. You see the weather forecast in advice there.
Yeah, it's a little wet out there now.
But metrics we often use are things like CRPSF, continuous rank probability skill score, and diagrams or rank histograms. Have you looked into those and comparing use of those?
Yeah, I have a paper that's in review right now, and we looked at reliability diagrams as well. We didn't look at continuous rank probability skill score or telegram diagrams. Those are more for continuous forecast, but this is just binary. An event occurs or it doesn't occur, and in that specific case is what I've looked at here.
Do we have any other questions? Okay, thank you.
Thanks.
So we have a little break of 10 minutes, but I just wanted to give a little summary. Don't leave. See you. Yes. A little summary of the first 3 talks that we saw, and the first one was on reservoir optimization, the second one was on the BCSD and spatial correlation, and the third one was looking at the predictability of binary events. And some of the questions that I had, actually, Derek, if you had any question for Derek, I think that would be a great time. I had one for you, which was based on what we saw, and we see how developers are working on the verification of the forecast. They're looking at the reliability, they're looking at the accuracy, and I think that one of your talk is one of there are not many that I see on reservoir optimization who people actually look and verify the forecast and the input into their optimization system. Usually people look at the output, not so much on the input. And is your tree approach taking advantage of some of the skill and the post-processing that we just saw in the two presentations? Or how is your pre-approach or optimization taking into extracting the skillful information in the forecast? Would you mind coming to so that we can hear you?
So in fact, you can put in whatever you have available. So if you have a post-processed ensemble forecast, you can put this in if you unbias it before. So that's of course preferred compared to to a biased forecast. But there's one important thing you need to do. If you start to do statistical post-processing and you just have like a probability distribution, that's not something we can use in the stochastic optimization approach. Now, that's one aspect, and the other aspect is the motivation for generating a tree out of the ensemble. So, first part here is to reduce the number of ensembles going into the optimization. So sometimes sometimes you may see within 50 ensembles that 25 ensembles do not have any rainfall. So they're the same. So there's no added value taking into account all 24. You can reduce it into a single one and aggregate the probability of all of them. So that's one aspect. And the other aspect is that introducing the branching points, that's making the optimization adaptive to the resolution of uncertainty. So when information comes in a forecast, at this point you can decide what to do. Just imagine a binary event. So you might have a precipitation event at time step 12 or not. So up to this point you don't know what to do. So you need to have a joint decision for both scenarios. And after this point you can split up at the branching point because you will observe the forecasted precipitation. So at this point the uncertainty gets resolved and you know what's happening in the future, and at this point you split up your decision. So you have one branch for the rainfall event and the other branch for the event where you don't observe any rainfall. So the motivation for the scenario tree, that's mainly because of adaptivity in the optimization.
And if there is more skill, for example, at day 1 and at 5 days the skill is pretty low, are you taking this into consideration in the optimization?
Yeah, that's taken into account because the spread in the ensemble is taken into account. So that means if you look at the forecast convergence score, so what you see at day 10 or 15, the probabilistic forecast becomes very stable because it's converging against climatology. So that's the reason why it becomes stable. So there's no, at a certain point, the probabilistic forecast has no added value compared to climatology. But that's okay for the decision making because there's just no additional information you can get out of a probabilistic forecast here compared to climatology. The important aspect is that this is for the decision making. This is much better compared to a deterministic one, which gets somehow chaotic after like 5 or 10 days. And then you just get a random realization of the future. It can be like, it may include a flood event, and in the next one you get in, it's not including this flood event anymore. Or maybe also the amount of rainfall in a flood event is changing a lot from one to another. So that's the disadvantage of using a deterministic one in decision making. For the first 5 days it's fine, but after 5 days it becomes somehow random. And also your decision becomes random.
Yeah. Thank you. Are there any other questions for Dirk? No? Thank you. Sorry, it's putting on the spot. Yeah. Okay. I'm still taking this opportunity to do a little advertisement. You may have seen that there are a couple of flyers around the room, and they're on the APEX, which is the Hydrological Ensemble Prediction Experiment. And this experiment is about bringing together the people that are creating ensemble meteorological forecasts, hydrological forecasts, and then putting it into users and user communication. This is an activity that has been evolving a lot in the last couple of years, and it can be very simple. You just run a couple of GCMs, for example, or perturbed weather forecast, and then you put them into a hydrology model, put them into the optimization. But what happens is really in the details, where what's actually happening is that there is some post-processing between the met forecast and the hydrologic forecast, so that we calibrate the ensemble statistically. And then once you go through the hydrology model, whether the probabilistic skill is moving forward or not, this is a different question. So there is another step of post-processing. And then when you put it into the reservoir optimization, or whichever is the end user, again, the post-processing is going to be very different for each of the application. And finally, you need to communicate that uncertainty. So there is this APEX experiment where we have annual meetings, and we also have some topical meetings on, for example, the application of ensemble seasonal forecast in water management. And I really encourage you to go. We have a blog in which there is about two entries per week. They're pretty short. And the subject is about people, for example, there are some flood events, and people are going to discuss how it was forecasted, for example, or what was the operational experience. Then there are some research projects. I really encourage you to go through it, and if you have an idea, you would like to present your presentation today, for example, it's easy to write a blog. There is some guidelines if you want to, and that allows you to also have feedbacks or to have access to a community of people that are very expert in the verification and application that we saw today.